Welcome back, and I do hope as ever you and your family are keeping well. So what we're going to look at today is colours of light. We're going to begin with a bit of revision of how we get colours of light from white light by using a prism, and you may have seen that in a previous video of mine on light refraction. We'll then look at what happens when we put coloured filters in front of different colours of light, and finally we'll look at what happens when we put more and more colours of light onto a white surface. Okay, so now let's look at another experiment we can do to show what happens when light hits glass and slows down. And this is light hitting a prism. Okay, so a prism is kind of, for us, a triangular shaped piece of glass. And this is a really famous experiment, and it's one that you probably all know about. Isaac Newton is famous for this one. And he was wondering what sunlight is made out of. So he was at Cambridge University, sitting in his room in Trinity College, and he had a hole in the blinds. I don't think he had curtains in those days, probably cloth was very expensive. So there was a hole in the blinds, and light came streaming in, and he held a piece of glass in front of it that was this sort of shape, a prism, and the light that came in, I'll draw it with a black pen if I may, so there's the light coming in from the sun, okay, did something really interesting, that when it hit the glass it slowed down, and if you draw all the correct normals and angles here, something really interesting happens, that the light splits into colours, and you get the red light bends towards the normal, and this is the tricky one, it then bends away from the normal, and down it goes. So there's the red. Green light did the same thing, but not quite. Green light bent towards the normal and then away from the normal. So that's green light. And finally, on my diagram, blue light, I'm overemphasizing it a bit here. Okay, did this sort of thing. Yep. And what he saw was a spectrum. Okay, a spectrum. Spectrum means, in this case, light ordered. Do you remember it's ordered in terms of its wavelength? That red is a long wave, green is a shorter one, and blue is a much shorter, or at least a little bit shorter wavelength. Okay, so what was Newton trying to prove? He was trying to prove, using refraction at this surface here and that surface there, that the light coming in from the sun that's very bright, and we'll call it white light. Okay, there we go, we have to use a black pen for that. White light, yeah, is actually made up of, and this is really weird, made up of colours. He suggests there were 7 of them. Yeah, red, orange, yellow, green, blue, indigo, violet. Okay, the spectrum, I've just drawn 3 here. And I think you're all familiar with this at the current period because of all the rainbows everyone's drawing for the NHS. I must say I've seen some of the rainbows that are completely the wrong way around and have got all the colours muddled up. But it doesn't matter, people are having a go. Okay, but this is the correct order. And it's the start of the way you can understand how rainbows form. It's not quite the way they form, but imagine that the prism is a drop of rain falling, and you can begin to understand that one of the processes that happens in a raindrop is refraction, splitting into the colours, and the other one, in fact, is a reflection off the back of the raindrop that makes sure that when you've got the sun behind you, the light hits it, refracts, and then reflects back at you. That's more complicated, but the main thing here is to see how a prism can cause refraction of light. Now, I'll just end by saying some scientists at the time said, but Mr. Newton, your prism has made colours. That's what it did. It made them. It manufactured them. He did something very, very clever. He put the prism in front of the colours, and guess what came out? it joined them all together, it refracted them in such a way that the three colours came out in one ray, okay, overlapping, and you saw white light. So he proved, using laws of refraction, that the light from the sun is a mixture of the colours that you've seen, okay, and the proof is if we put them on top of each other and mix them back up again, we go back to white light. So again, if you were with me in the classroom, and it'd be wonderful if you were, we get a prism out. I've got a high dispersion prism here, a really good one, small, but it works really well. And what we do is we get some bright sunlight through the gaps in the big curtains I've got, and we'd split it up into the coloured spectrum. And I normally turn it towards one of the boys or the girls' shirts or blouses, and we use that as the screen. And what's really cool is, you have to be careful with the intensity, is if you've got those colours coming in off the prism, you can move your eye across them. You need to be certain that you're not looking at really intense light, okay? And you can actually see the red, green, blue and the other colours as you move your eye across the spectrum. But shame you're not here, so what I'll do is I'll just quickly demonstrate that by blocking off the light from my projector and just leaving a slit, a gap like Newton had, and holding up the prism, and I'll show you the colours that we get. So if you look there, you'll see a lovely spectrum, and you see the colours of the rainbow and everything. Okay, so I've got a slit of light, and I'm passing it through the prism, and it's dispersing it into the colours of the rainbow. Good, so you now know that white light is made up of three colours, some red, some green and some blue, at least three colours, okay, and we'll keep it simple and deal with those. And that they're different because they have different wavelengths. Red is very spread out, green has a shorter wavelength, and blue has an even shorter wavelength, the gap between each peak in the wave. So we add red, green and blue together and we get white light. So what we're going to look at now is what happens when we shine white light onto surfaces. So it's pretty obvious, white screen, white piece of paper, my white shirt today. If we shine white light at a white surface, all of those colours get reflected back at you. So if I draw here a white piece of paper, and we shine in white light, so in goes white light, we get white out. Now, what you've got to remember is that that white is made of red, green and blue light all added together. Okay, so what it means is that white surfaces, and I'll write on this that this is white, like my shirt or a piece of paper, white surfaces reflect back every colour that you throw at them. Okay, but what you need to know about is what happens if the surface is a different colour. Okay, so let's look at a surface, for example, that is blue. So this is blue. Oops, a bit difficult writing sideways. Okay, so there's our blue surface. Maybe I'll do that. Now, think about it. If white has red, green and blue coming in and you see white coming out, then if white comes in, then white's reflected. Then maybe with a blue surface, like this folder here, you can use a similar bit of physics. We're shining white light in, and you're seeing blue. So, in goes the white light. And you always remember that white light is a mixture of red, green, and blue. But when you look at it, okay, you only see blue. So it means that it's throwing back at you, or more correctly, reflecting at you, blue light. So what's happened to the red and green? Well, one of the ways of showing you that is holding up the folder and saying, look, this is quite light and this is darker. So if this folder is darker, what it's done is it's absorbed the red and green. That's gone into the folder's surface and warmed it up slightly. But the blue, it's reflected back, so it's not absorbed blue. So isn't that weird that a blue folder is blue because it doesn't like blue light? If you shine blue light at it, the blue light comes back at you. Okay, and I always ask the question of students what they think about trees. Okay, trees with their green leaves. Do trees like green? Well, they don't. Okay, I'm not a biologist, but clearly there are some wavelengths, particularly in the green end of the spectrum, that they don't need. So a green leaf on a tree must be absorbing the red and blue, okay, and reflecting the green back. So the colour that you see of a surface is the colour that comes onto the surface that's reflected back at you. Okay, it's a little bit more complicated if you do something like shine blue light. So there's blue light coming from my projector now, and we put something that's green in the way. Okay, so that's green. And if I put that there, it doesn't really work with the projector very well because there's a lot of background light. But I'll draw it instead in a different way. Here's a green surface. Okay, so we're going to make that, let's put a big G on it because I can't write sideways. That's a green surface. And if you shine blue light on that, so in goes the blue. Think about what green surfaces do. They reflect green light. Reflect green light, they don't make it. So in goes the blue and it's absorbed and you get nothing out. Okay. Now, I'll show you this a little bit later on maybe in a different experiment, but this is counterintuitive, isn't it? Okay. A lot of people say, oh, well, it'll appear blue. No. In a completely dark room, okay, which I haven't got here at the moment, if you take a green surface and shine blue light at it, it won't send any light back. It'll appear completely black. Now, I'm going to put up a link to my YouTube video on, it's an FJ's Physics one, on colour physics, and I'll show you there in that video exactly what happens when we do that, when we shine different colours of light onto different coloured surfaces. Right, now let's look at transparent objects, and I'm going to call them filters because we're going to look at transparent objects like these bits of plastic, the sort of ones they put in front of stage lights to give them colour. Okay. Well, this is again a bit counterintuitive and not very obvious. If you remember, I'm writing at the moment on a transparent material, and because it's completely see-through, it lets all the light through. Okay, so it's kind of colourless. So we shine white light at it, red, green and blue, and red, green and blue come straight through. But what happens with something like a green filter? Okay, so I'll just draw here something that represents our green filter. Fill it in, not a very good pen, there we go. Okay. And remember that what we're doing here is we're shining white light in. So in goes white light. And you must always remember that white light is made of the three colours, red, green and blue. And if you remember, when you look at this, it's darker than here. So it's not letting all the light energy through. And as you might guess, what it's doing is absorbing the red and the blue. It's not letting those through, and the filter's warming up slightly, but it's letting the green through it. Okay, So a green filter, think of the word filter, is something that filters out everything apart from green. Okay. So if we were to shine just green light at the green filter, it would say, I don't filter out green light, so green would go straight through. So I sometimes draw this in my class and say, what happens if I put another green filter there? Okay, the light basically goes straight through because green filters let green light through. So, you understand that? So what happens if we switch to blue? Okay, so we'll take a blue filter and my projector is feeding white light into the blue filter, so in goes the white light. And I always find it helpful to write on this that that is red, green, and blue coming in. And I find students find this really difficult. I'm not sure why, but I'm trying my best to help you here, okay? So it's a blue filter. Blue filters let blue through, so those two are absorbed, and through comes just the blue light. Okay, but now for the interesting bit, and the bit I was trying to get to. What happens if I now put a green filter in the way? So here's our green filter. Green. And we're going to shine the blue light into it. So in goes the blue light, straight ray. Okay. Now, remember that green filters don't make green light. Green filters only let green through. But there isn't any green hitting it. So it can't let green through. So nothing comes out. And that often surprises students. They expect something. They expect the blue to be turned into green. Okay, but this green filter only lets through the wiggly waves of the right wavelength for green. Now, how do you prove that as a teacher? I really love doing this little simple experiment. Okay, here's our blue filter. That's that white light coming into our blue filter. And here's our green filter. And I often ask people what they think is going to happen if I overlap them. Okay, and they come up with some crazy colour like purple. There we go. I hope you can see that that is completely black. It's not letting any light through at all. So finally, I've overlapped 3 primary colour filters, a blue and a green and a red one. Can you explain what's going on here? So we've done a lot on colours and filters, and if you remember, filters remove colours, so physicists call that subtractive colour mixing. Okay, it's actually the same thing you do when you do paint and you mix paints. Remember, when you put blue paint down, the blue is absorbing all the other colours. Okay, and as you add more and more coloured paints, you remove more and more colours, and it goes darker and darker and darker. Okay. But let's do the opposite now. Let's imagine we're at a disco or what have you, where there are bright coloured lights. Okay, and it's a tricky one to get your head around this. But what we're going to do is have some colour on us and then have more coloured light and more coloured light. So we're going to add colours. We call this additive colour mixing. So we're going to look at what happens if we shine a blue light on a white surface and we shine a red light and we shine a green light. So if you think about it, we're throwing at that white surface 3 different wavelengths of light, okay, and they're going to reflect back, and we'll see what happens when they overlap. But just before we go into the lab and do the experiment, do you notice that green and blue here are overlapping? Wonder what happens there. Red and green are overlapping, and that gives I always think, even as a physicist, a really surprising result, because we're going to get red and green light coming back at us. And here, blue and red overlap. And in the middle, red, green and blue overlap. So let's go into the lab now and do an experiment to see what happens when we add colours of light. So I'm in the laboratory now, and I've got a piece of apparatus that I love to show students. What I've got here is a thing that gives out red, green or blue light, and it passes through a hole to make circular shaped beams of light, and there's a white screen over here. So it's a very bright day outside, so I hope this works. But let's shine some red light onto the screen so you can see the red there. And let's put on top of it more light. So let's put some green light on top. Now, what we've got hitting the screen there is red and green overlapping. And I think I said to you earlier on, the result you get here is really, really surprising. Okay, we're not using filters, we're not using paints, which are filters, we're adding light. And if green and red light go into your eye, you perceive that as yellow, isn't it? It's an unbelievable thing. It still surprises me to this day. I find it really hard to think that red light energy added to green light energy makes yellow. Okay, I'll just turn the green down and turn the red down and now have some blue light. Okay, and let's now add some red light to that. Okay, so as expected, you get the blue and the red light, and in the middle you get blue added to red. Okay, and that colour is not purple, it's magenta. So let's now try with some green and blue, and when they overlap you get a lovely colour which we call cyan. It's a sort of turquoise. But finally, let's add the three. So 3 primary colours added together, and I don't know how well it comes across on the video, but you've got your blue, red and green. Green and red is yellow, red and blue is magenta, blue and green is cyan. And I really do hope you guessed what would happen in the middle. It's obvious, really. We've got green and red and blue light. We've got the 3 primary colours. That's what makes up white light. So there in the middle, where they overlap, you see a little shape that is white. So I love doing that experiment, and I always find it's really counterintuitive, the colours you get. Some people find it difficult to remember this, but it's the ideas that count. So we're putting 3 lights onto a white background, and the blue and red add up and make magenta. So I can sort of attempt to do that here. Okay. The blue and the green add up, and I haven't really got a good pen for that one, but I'll try. Here, I don't think the highlighter pen works. Cyan. Okay, so what I'll do is I'll just black it in. Cyan. And the really surprising one is when red and green overlap. And again, I'll try a highlighter pen, but I don't think it works very well on this surface. You get yellow. Okay, and again, I'll just block that one in. But, of course, and I hope you know, that in the middle, where the 3 colours overlap, here, right in the middle, you get white light. Now, just before we finish on this, I think you've probably seen magenta, cyan and yellow before. They're used for printing. And if you have to replace the toner cartridges in a laser printer or something, you'll be putting in black cartridges so they can print just black on white. But they also have a cyan, a magenta, and a yellow cartridge. Okay, not going to go into the detail today of how those mix to create the other colours, but maybe if you open a packet of cereal or something like that that's printed, some newspapers have it, hidden on the inside is a little test card, and you can often see those colours, and it's how the printer checks that the colours are printing properly on the packaging. So I do hope you found that lesson both interesting and useful, and you now have a really good understanding of light. Anyway, I'll be making another video lesson soon, and I look forward to seeing you then.